We're up to episode 13 of our retro core development. This time we look at hardware addressing techniques. We take a look at the usefulness of MAME, then we finally launch our core on the MiSTer. So let's just go over the schematics again for the Tank Battalion game. Good thing is it's only 2 pages. So we've got our first page here and our second page there. And you'll remember that this part here was the timer. So we got our crystal timer there. We've got the horizontal counter circuit and our vertical counter circuit. And that's making the counters for our display circuitry. And it's also used for other parts in the design too. If we go back up to here, we've got our CPU, 6502 CPU. We've got 4 ROM chips. We've got 6 RAM chips, which are effectively 3 8-bit RAM chips. They're paired up, 4 bits each. We've then got our familiar latch that takes in data for the display. It then goes through our character prom, then our renderer, pixel renderer, and then throughout into our screen display. Now this bit here was our bullet renderer, and we haven't covered that yet. We're going to cover that in the next episode. But what I wanted to cover in this episode was the address decoding system, and that is this bit down here, as well as another bit up the top. And this allows us to access our RAM, our ROM, and also the peripherals. And we're going to cover exactly how that works in this episode. So the first one is this bit up here, and it's this selector chip that is selecting which ROM chip we're going to access. So these here are the enable pins, active low chip enable pins. One for each of the ROM chips, and we've got our 4 outputs from this particular selector here, and we've got an enable chip for this enable pin for this chip, and then we've got 2 pins that are connected to address lines of the CPU. Now, first thing to mention is, if you remember from the last episode, in the design, the actual design, we're sharing our resources between the CPU and our display device. So we were using these chips to make a counter to look through the display circuitry. Now this is also happening with our access to the chips by using this Phi2, which is the CPU clock. And in our design, what we're going to do is we're just going to get rid of any link to Phi2. And we just have a straight pass through. So A13 is the pin for not ROM, so active low ROM, and then depending on the address line A12 and A11, we choose which particular ROM chip we are wanting to access. And we'll have a look exactly how that works a little bit later when we look at the binary accessing of each of those. Down here, very similar, we've got this Phi2 that's also doing some of the timing for these for the RAM and the peripherals. Again, in our design, we're just going to disregard that bit. This is the read and write pin of the CPU, and this goes through and becomes a WO dash or not WO. Now the interesting thing with that is, I think that is a write enable for our RAM chips, and this goes to just that WO dash, and then up here we've got this curious line that is our write enable for our RAM, just connected to nothing. And I'm almost certain that's just a mistake in the schematic, that if you connect that up to that particular WO dash, that works just fine. And certainly in my FPGA design, that works really well. And even in the breadboard version that I did. So I'm almost certain that is what they intended there. Here we've got a selector, so same as above, a 139, 2 inputs and an enable. So this is effectively saying if enabled if we're not choosing the ROM. Then if we're not choosing ROM, we're probably choosing RAM. And then it uses pin 11 and 0 of the address bus. And the difference between AB11 and A11 is passing through these chips. So if you remember, we're actually not going to use the AB designation. We're going straight from the chip into these in our design. So that's work RAM 0, work RAM 1, and then video RAM. So that's how we access those. And then these are some peripherals. So that's dip switch, input 1, input 0. This is the watchdog reset. This is the interrupt acknowledge, and then out 1 and out 0. And so effectively these are dip switch for the game. We'll cover what those are. This is the controls. This is the sound, and then the watchdog we're going to have a look at now. So the watchdog's an interesting feature in arcade boards. Effectively, imagine you've got an arcade board that's a little bit flaky and goes wrong every now and then. So you've got all your arcade games all lined up in the arcade. Something goes wrong. What you don't want to have to do is pull out the arcade machine, pull it out the wall, and power cycle it, plug it back in and move it back in, especially if that happens a number of times. That's all lost revenue. So the clever folks who designed arcade games, what they did was they've created this timer, and it's triggered by the V-blank. So every V-blank we're having a clock cycle, and this LS161 is the same as our timers for the horizontal and vertical. And we've got this watchdog reset number. So effectively we've got a number, I'm not exactly sure what it is, but it'll be, you know, the maximum of this counter. So probably 256, so 256 V-blanks. And if it gets to that maximum number, we carry, and the carry is ANDed or NANDed to become active low, and that creates a reset for the 6502. However, the software is constantly writing to this watchdog reset, and it clears it. And so as long as we clear it within that 256 V-blanks, we're good, and it's not going to reset. So the software is going to always have a cycle where it's doing this watchdog reset. So it's quite an elegant way of allowing the system to self-monitor itself and just reset if anything is wrong. Up here is exactly the same as our power on reset that we implemented in our last episode, except this is a hardware version. So we've got capacitor, resistor, circuit here that's just creating a power on reset once we turn the device on, and gives the 6502 a nice way of starting up in a perfect way. So now we're going to have a look at exactly the addressing of these and what we are addressing with the input output. So in order to learn a bit more about the Tank Battalion game, in fact any games that you want to know about the memory map or the controls, I showed in a previous episode this arcade restoration website, and it's a really great resource. It provides lots of information about the game, what kind of resolution it's got, the year, some information about the MAME files. And what we can do is, if we go down to memory map for this game, first actually we could look at the dip switches. We'll look at the dip switches in a bit more detail in a further episode, but actually in terms of hooking them up, we're going to do that this episode. But what do they do? So I guess we've got 8 in the actual thing. I think we've got a bank of 8, only 6 are used. First 2 aren't used, and then number 3 tells you how many lives you're going to have, whether it's on or off. And then we've got these 2 switches, 4 and 5, and how the combinations of those give you different bonuses. And then 6 and 7 is how many credits you get for a coin. And then the last one, number 8, is what kind of cabinet we've got. So I set all these to 1, which basically puts us on free play, and we get a good, I think we get a bonus of 10,000 and 3 lives. So if we go back, we can look at the Tank Battalion map here. And so that's what we've got. We've got the addresses, how long they are, what they are, the functions, and then a little description about it. And then this particular thing is if you're actually burning the ROMs or want to check your ROMs compared to the official ones. What do they look like? What are the files? How big are they? You remember in our game we've got our graphics ROM that we've been using all the way through. We've got our game ROMs, and then we've got our color PROM. So that's where they are there. Now I've broken this down a little bit simpler, and we're going to look at that now. Basically this same info, but just broken down a little bit. So here's that same information. We've got the address range of the game, whether it's a read-write, what the function is, and then a little description that's pretty similar to the function. So the first thing we've got is we've got our work RAM 0, which is location 0000 up to 3FF, and that has our 0 page in it. Work RAM 1 is just another bit of RAM from 400 to 7FF, and then we've got our VRAM, so our screen memory, from 800 up to BFF. And then after that we've got our peripherals for a little bit, so from 0C00 up to 0C1F. And we can step through what that is, but we've got input 0, input 1, and dip switches. We've then got our ROM, and so it's from 600 up to 7FFF. And we've also got the same ROM from E000 to FFFF, and it's the same ROM, it's only done once, but the way it's connected, it sees it twice. And actually the game program will remember the reset vector goes FFFC, FFFD, so it looks there, and the actual program is written to this 600 up to 7FFF area. So we never go up to here once it starts. So that's reading. For writing, we obviously have the same, but we have our write enable enabled on the CPU. So the work RAM can both read and write. So work RAM 0, work RAM 1. The video RAM, obviously same thing. We can read and write to the video RAM. In the same space that we had our inputs, we've now got outputs. So we can read or write to different areas based on whether we've got that write enable, and that's hardwired, as we're going to see. The C0C10 is the interrupt acknowledge, and that's something we'll just get into in a future episode about what that's doing. The 0C18 is the watchdog reset. So that's what we talked about, is effectively that's a way of making sure that the system isn't going to reset all the time. So that's good. Now for the ROM, this 600 to FFFF, we can't write to that. So although I've got it here, it's not happening. It won't allow you to write to that. So that's that. So the inputs are effectively, what we can do is have a look at the schematic, just have a quick look at the area of the schematic that's showing us that. So firstly, we've got our part of the addressing circuit here. And so we've got our VRAM, workram 1, workram 0, and here are our dip switches, our input 1, input 0, output 1, output 0, watchdog. And what we do is we go down onto the next page, and this is our dip switch area. So I don't want to cover necessarily what this chip is doing this episode. We're going to code this into our MiSTer core in another episode, but effectively we're addressing with that enable, as you saw on the previous page, the dip switch, and then once we do that, this chip is taking one output for whichever one is being addressed by the C, B and A down here. So we can, the program is basically looking up 8 bits once this is enabled and getting an output. So it can say, you know, how many lives do we have in this game, and it'll output Y. So that's how it does that. Similar thing for the inputs and the outputs. So we've got in 1 and in 0, and these are connected to something, switches of some sort. And then we've got our outputs here, and our output we said is, one is sound, another one is like LEDs to show you've put in, or not LEDs but bulbs, to show you've put in a coin. There might be some indicator that you've put in a coin. We've got our power on reset there, and we've also got our non-maskable interrupt on, and that's quite important. That's what gets the actual game going. There's an attract mode which starts up, which in this core at the moment, when we start it up, it gets to that and it just stops. So we've got our out 1 and our out 0, and that's how those are addressed. So if we go back to the memory map again, so what are the functions of these? So basically each one is individually addressable. So for the in 0, we've got our joystick controls up, left, down, right, shoot. So that's C00 down to C04. Then we've got our coin switches, so that's a coin being put in. We've got a service mode button, and then these are not used up to here. And then in our in 1, we've got player 1 start, player 2 start, and another test toggle. And then on C18 downwards, we've got our dip switches. So that's everything we need for our inputs. And then our outputs, a lot of these on out 0 are not relevant now. Obviously the outputs require the right enable as well, whereas before we didn't have the right enable. For the ins, we do have the right enable now with the outs. So our out 1s are basically audio mostly, and then this this demo interrupt enable. And then we've got our watchdog reset as well. Now, as I said previously, we're not going to do anything with the watchdog reset in our circuit because we don't need to. So we'll pretty much just ignore that. Now this circuitry that we saw before, if we go up here, this circuitry that we saw before, we're using these chips here to create the addressing of enabling each of these states or chips. Now what we could do, they all are effectively just addresses in binary, and what we could do in Verilog is very simply just check for the address and say, does the address equal this address? And if it does, you're trying to access this function, and that's how a lot of cores do it. So one thing I've been conscious to do so far is effectively recreate the core using the same schematic that we've got for the actual game, and we don't need to do that. We can actually simplify it a lot in the code. And what I'll probably do is get the core working exactly as the schematic has it, but then eventually we'll just strip all that out and just show how simply we can do it with just these, you know, lines of code where instead of instantiating chips, we're just you know, checking for these states. And that's where you can look at the MAME code and effectively quite quickly port it over. Now sometimes you may not be characterizing it correctly because there might be some shortcut there, so you don't necessarily always want to do that, but for a game this simple there's certainly no problem doing that whatsoever. So again, in terms of the addressing, obviously workram 0, all zeros, and then what I've got here is I've highlighted in red the bits that are important to check for. So 400 or 400 hex would be that bit there, then 80 there, C0. So these bits here are very important. And then for the RAM, and then the C00, and then for the ROM, actually it's this particular bit here, bit 13, that's important then. If bit 13 is 1, then we're looking at a ROM. As I said before, the ins and the outs are the same, but we've got the write enable activated as well. So we're going to look at MAME for a little bit. So I've installed MAME from the internet into the directory MAME on C, and the important thing is obviously we've got our files there, and then we've got ROMs, the ROM folder, and we've got our ROMs in here. Now you can have them in zip format, or you can unzip them as well and just put them in a directory like this. So this is our tank battalion directory. Under MAME, tank battalion is called tank bat. So I've put it in a folder there, and then those are the ROM files. We'll remember that these are 2K, I think, is our character ROM. L3 is the PROM, color PROM, and then we've got ABCD, which are our game ROM files. So that's the only ROMs that we've got for this particular game. So that's that, and then what we want to do is fire up MAME. So we get a command prompt up, and then we want to do cd / MAME, and then we're in MAME. Now what we want to do is we want to do MAME 64, and then the name of our game, and we want to put debug on there as well, and we set that going. And we pull that in here, we make it a bit smaller. So that's our screen. Here we've got the debug window. Put that in there, and we're also going to make a new memory window there just for fun. And this memory window is good. We can look through the memory of the complete hardware. All the ROMs start here in E, but I think there should also be mirrored down here in 6, as we talked earlier. And in previous episodes we've got from 6 to 7FFF is the ROM, but it's also E to FFFF, and it's the same. Up here we've got our program. I'm going to do a short bonus video in a future video just to show a little look at the disassembly of the Tank Battalion game, just the startup sequence. It's not particularly relevant for what we're going to do. We don't need to know that, but when I was looking at getting the game working, I obviously wanted to work out if what it was doing and how's it interacting with the hardware and everything. Turns out on Tank Battalion you really don't need to do much looking at the code to make sure the hardware is going to work. Sometimes you have a feature where the hardware is looking for specific things, and if it can't find, if the code doesn't totally match what the hardware's got, then it won't work. And it was a way of making sure that bootlegs weren't going to run. But this is so early, I think they hadn't implemented anything like that in this particular game. Up here we've got the disassembly of the program, which is basically the disassembly of this hex here. A good way to export this to a text file is if we say DASM, and then we say the name of the text file, so tankb .asm, then we say the location that we want to disassemble from and how many bytes we want to disassemble. It says dump, data is dumped successfully. Now if we go back out to our MAME, you'll see that we've got this tankb.asm file, and if I just open that one, that's the disassembly of the game we've got there. Now there are some small features which don't quite work. For example, right at the end we've got the reset vector, and in this case we've looked at reset vectors before, and we always had that F800 in previous episodes. This time it's actually 7D43, which is where the program starts, and this is actually interpreting this to be, you know, a particular instruction, but it's not an instruction, it's just the reset vector. And we've got similar vectors for interrupt vectors, which we'll see in later episodes, but so it doesn't all make sense, but away from here it actually does. So that's how we've exported this disassembly to a different file for us to look at later if we want to. So that's where the program begins. Now in MAME, now under the debug, we've got a few options, all dependent on function keys. So if we wanted to run the program from now, we'd press F5 and it would launch into it. Or we can step through each individual item. If we press F11, we go very slowly through each one. And if we want to know what's exactly going on, we could do that. But obviously that is very, very monotonous, and we'd only want to do that if we're actually looking for specific things. You can set breakpoints to go to if you're looking for specific parts in this code and what it's going to do next, or you can do things like go to the next hardware interrupt, go to the next VBlank, which is effectively the next screen, or you can go to the next CPU interrupt. So we're going to go and look at the first hardware interrupt, which is exactly where our hardware is going to stop when we look at that. So if we press F7, you can see there we've got a little introduction screen, and then it gives this attract mode of the score, and then bam, we stop there. We've got a familiar walls of our maze. We've got the red bricks of the walls. We've got the beginning of a score, players, how many tanks we've got, and then how many enemies are going to be on the screen or we have to shoot down. So if we want to start that again, we can do F3. We'll restart the whole thing. We can stop with F11 again, or we can just carry on with F3. And then it can go all the way through. This time it's probably not going to stop, it'll just go all the way through into the game. And there you go, that's the attract mode of the game running through. So MAME is really good at obviously, you know, we can see what MAME's doing, we can stop it, we can restart it, and it helps us just to see what we need to expect on our hardware when we're going to be running it. And if we're looking at specifics of the code, it's really good to go to certain parts of the code and see what's it doing, how's it interacting with hardware, and what's it doing in the actual program as well. Okay, I'm on the GitHub, and we're going to go into episode 13. And in episode 13 we've got 3 folders. We've got Tank B FPGA CRT, the VGA version, and a sim. So this is the MiSTer CRT native arcade display. The next one is the VGA one, and then the sim one is we're going to have a look at some examples of output from the simulator. So first let's go into the CRT. Okay, so if we go down to TTL chips, the only thing I've added here is the LS42, and that was the selector chip. So effectively what that's doing is, if we look back at the schematic, so we've got our circuitry that we saw before. This is the 74LS42, and it takes 4 inputs, and then it has a number of outputs depending on what inputs are here. So in terms of the logic, the truth table for that, this is the truth table for the 74LS42. 4 line to 10 line decoder. So 4 inputs and then 10 outputs, and depending what the inputs are, it selects an output, and the output that is selected is low. So immediately that rings alarm bells that this is for chip selects, so perfect for addressing different chips, be it memory or any other peripherals that we've got in our circuit. So you can see here, this first one here, if everything's low, 0 is selected. If A is high and everything else is low, 1 is selected. So it's really just a counter here through there, your typical binary counter, and then output 0 to 9 becoming low. So back in our code, how we're doing this is using a case statement in Verilog, and the case statement really just looks at what's the input. The input, you can select each different case explicitly, and depending on the input you can select what the output's going to be. And for OCD people amongst us, myself included, sorry for this being shifted over, very frustrating, but I'll fix that on a future upload to the GitHub. But yeah, it's a pretty simple construct there to get our inputs to outputs. So that's the only change in the TTL chips. Next is if we go and have a look at the ROM. The ROM file is exactly as we've had it before. The only difference is I'm including 4 ROM chips. We have 4 ROM chips in our design, and each one needs to load a separate ROM file. So I've got 4 different ROM modules with, explicitly stating the file. You could use the same module with language to include this as like an external input. That's one way of doing it. I'm just not doing that here, just for simplicity. It's a bit easier to read this for us beginners. Other than that, really nothing any different at all. We've got our character ROM and our PROM here as we had before. Next we've got our RAM file, and our RAM file is effectively the same as it was previously. We've got our single port RAM and our dual port RAM that we've seen before. The only difference I would say on this one is, as I'll explain a bit later, I have changed the write enables back to being positive. So in our design, and typically a write enable is write enable low, but it just so happens that the way addressing works in Verilog, or even VHDL probably, it just helps for the logic checks for it to be high, and I'll explain why in a minute. So I've taken away the reversal of this as it was before. So other than that, the ALU, the clock modules, the RLOT module, CPU module, all still exactly the same. I suppose we could talk about the actual ROM files. So as previously done, I've taken a hex file and I've converted it into a single entry per line text file. If you don't remember how to do that, that is in a previous episode. I showed how to do that very early on. We just need to do that to get that loaded into the software. There are other ways of doing it, but this is the simplest way of doing it for now. Obviously, when we put it into the MiSTer framework, we're going to work out a better way to do it long term. But it's a simple way to do it when we're not using the MiSTer framework. So everything else is still the same, and then we'll go into Tank B FPGA and just step through that a little bit. So first thing to say, I've added some wires here specific to the modules we've added. So this is for input output, so that's dip switch. Those wires are just not being used, but I'm not leaving them blank. And then we have our input 1, input 0, watchdog enable or reset, output 1, output 0. These are ROM outputs and these are RAM outputs. this is our dip switch input and our in 1 and in 0. So we haven't created the circuit for this yet. So all I'm doing is creating a known state, a beginning state, to feed them in. At the end of the day, we just want to have the startup sequence going in our core at the moment, so not doing too much interesting here. We did see earlier that the dip switch settings are all set to 1 to have certain characteristics of the game going. These wires here, again, are just being used as dummy inputs for now. These actually become the inputs to the peripherals when they're actually set up with the chips later on, but we're not going to do that this episode. Underneath there we've got the beginning of our address decoding. So if we pull up the schematic again, up here is the first part of the address decoding. So choosing the ROM, remember we've got 4 ROM enables and we need to choose those based on this A13 and the A12 and the A11. So here we've got essentially this here, not ROM is linked to A13, and then we've created this output C31Y. Y is the output to that 139 chip. So 11 and 12 are the inputs, not ROM is the enable, and then the output is the that there. Then what we're doing is we're saying, splitting those out, we could put all of those into there as that output as a concatenation, but just for simplicity I'm creating a 4 bit deep wire and then breaking them out as to what they are. So that's the chip enable for each one, as we can see in our code here, chip enable for each one, and then that's the output. Underneath there we go to the lower part of the address decoding, so we go down here, so that's this bit here. Again, as I said before, we're getting rid of the timing of the Phi2, and also the ROM and the H2, I've just blanked those out. I originally had those in there, we're just getting rid of those now. So that's it's describing that other part of the 139, the second part of it. We've then here got the write enable, which is linked to the read-write pin of the CPU, as we saw there. So that's the read-write there becomes the not write out, which we remember is connected up here, even though it's not showing. Now the interesting thing with that is when we'll see a bit later, this prevents writing if the ROM is active. So in theory, not that it would, but the chip could send that as being high, but this doesn't allow that to happen. And then we've got the we set our wires here to be not VRAM, not WorkRAM 1, and not WorkRAM 0, and that's the output of this D41Y. So that's here, the D4Y output, and then we go down into this 4F. So F4 here, we're instantiating the LS42 module we just saw, inputs being these, outputs being all of those. And in some of these, when you'll see I've commented an address bus, and now it's A, what that is to do with is in the original schematic, you can see address bus here, address bus. Now the address bus is everything on this side of these selector chips, and address, or the A, is everything the CPU side. Now you remember we said we were going to get rid of using these, even though I've still got them in the design. Basically everything from the CPU passes through here directly into here, so the ABs become A's, and we're not using that anymore. The video circuitry is separately getting its counters from here itself, and that's why we're not using those with this timing here. See, this creates a timing here, which is switching it back and forth, as we saw on the previous episode. Then if we go down to the next change, here, this is the L2 chip, or the 2L chip on the schematic. This is the address circuitry input, and all I've done is I've changed, we had a different variable here, I've changed the name to display D in, just to be a bit more explicit there what that's doing. Then if we go down to, we've seen all this stuff before, no change. We're down to our CPU. I've just changed some of the labels here for inputs and outputs. CPU data in, CPU data out, and that's there. So pretty simple what these are then going to be doing. We've got our read write as we had before. I've changed this to, this was set to 1 before, the maskable interrupt, and that is now NIRQ, which is actually in the circuitry. The next thing we'll be adding in one of future episodes is changing this one to one of the variables. But we'll leave that for now. The non-maskable interrupt, we'll leave that as just 1. Under here we've got our instantiation of the ROMs. Nothing special other than the fact we've got 4 of them, and we had to explicitly call them each a module, as you saw. The outputs to these are named ROM1A, D out, B, C, D, D out, so we know the data coming out of those is pretty clear. Next is we're putting in our RAMs. So we've got our 3 RAMs you've seen. We've got our work RAM 0, our work RAM 1, and our VRAM. And so work RAM 0 is this one. Now people may be thinking, why have I got this one as a dual port RAM? Makes sense why the video display here is dual port RAM, because we were accessing it from the video display circuitry and the CPU. However, don't forget, I haven't introduced yet the bullet circuitry, and the bullet circuitry is looking at the lowest part of the 0-page RAM, and it's also a display circuitry connected to that too. So we have 2 parts of this memory that is connected to the display circuitry, or 2 different parts of the display circuitry. So this bit is also connected, so this also needs to be a dual port display. Next episode we're going to look at what this bullet circuitry is doing and why it needs to be connected here. The work RAM 1 is simple, it's just connected to the CPU, so it's a single port connected to the CPU. Now, something I mentioned earlier was I reversed the write enable for the RAM, and the reason is here. You can see here we are checking to write to this RAM. We need 2 things to happen. We need the write enable to be active, and we need the correct RAM selected to be active. And we're doing that by saying if this equals 1. And these are both low, so we're saying if this is, and we're making it opposite with this exclamation mark. So if this is low and this is low, both opposite, 1 and 1 equals 1. And therefore 1 goes into this input to have a write enable. If we don't have that if this write enable is now, the other way around, it becomes very difficult in the actual RAM to get these 2 to be true at the same time. There is no, at least as far as I know, it's very difficult to get the opposite of an AND gate. And so that's why I've done it this way. There may be other ways to do it, but I think when you look at a lot of Verilog cores, there tend to be, people tend to do it so the write enable is positive, and I wonder if they do it because of this. And then after that we've got our outputs. So we've got our one output is RAM, the other in this case is our bullet out. Again, RAM out, VRAM out. So again, quite explicitly labeling those just to be a bit more sensible in knowing what they do. the inputs are obviously the CPU data outputs, so that makes sense as well. Then down onto the address muxing, and so the interesting thing with this is if we look at the schematic again, we can see how the CPU is connected to the ROM, the RAM, and also the display circuitry. So we've got the address lines connected and then the data lines connected. In an actual circuit, what happens is the CPU will help select the chip by the enable pin that we've seen. If the chip is not enabled, then the data will not be on the bus. In Verilog, effectively what we're going to see is the chips are always all connected and the data is all on a virtual bus, but we're selecting which one of those buses to take and use. So if we go back to the code, that's exactly what this is doing. So it's saying the CPU data in is chosen based on which of these chip enables is active. So is A1 chip select active? If it is, then chip data in should equal the ROM data out of ROM1. And it just goes through this check for each one. So is ROM B1 chip select enabled? If it is, then use ROM 1BD out as the C data in. So it's a bit different to how the actual circuit works, where the chips are either on or off. In this case, they're effectively all on, and we're just choosing which bit of information to take in as our data in. Now the reason why we've got these exclamation marks is because all of these are active low, and we want this to be true. So 1 equals true, so we need to reverse all these to say which one of these is true for the data in. Now previously I discussed how the different memory addresses are all actually just binary numbers, and how we could look at the specific binary number, and depending on certain bits we could do all of this selection ourselves. And that's what the code is doing here for the video memory. So it's a very simple selection for the lower work RAM or the video memory, is saying this VA is the video address, and we're saying of the bits 11 down to 4, if all of them equal 0, then we are working with the work RAM 0, and if bits 11 down to 10 are 1 0, then we're obviously working in the 800 hex, so that would be the VRAM area. So essentially, instead of having up here our address decoding here, so instead of having this as our address decoding, we could just have that exact same thing, where we simplify these chips out to say what is the address in terms of bits, and then based on those, these chip enables can be true or not, depending on which are true. And what we could do later on, as I said, we can simplify our code to get rid of all of these chips and just do that instead. And it obviously makes that code much smaller. So I want to step into the TankBSim, and the TankBSim is effectively the same. These files can be plugged into Modelsim. Everything's the same except we have two versions of the sim. Sim A is specifically what we're doing is, you'll see here we've obviously we don't need the clock, so we've got rid of that one, so we grayed that out. And then if we go down to the 6502 CPU, that's gone too. So I've grayed that out because what we're doing is we are explicitly driving the address bus with certain inputs, because I want to test if our enables, basically if our address decoding circuit is working. And what we can do is we can explicitly put on the address bus certain locations, and we'll see what happens. So I've previously run this in Modelsim, and this is the output that I got. So for our address drivers, we've got 0, 0, 4, 8, 0C, 0, 8, and so on. So this was what we had. 0 to 3FF was the RAM, and then another set of RAM at 400. 800 was the VRAM. Then we had these C00 up to C1F. These were some peripherals. And then we had the ROMs from 600 up to 7FFF. So let's see if that all works out. So yes, so at 00 we've got work RAM 0 is enabled. Remember, enable low. When we go to 400, we've got enable low for work RAM 1. And then 800 was VRAM, so that's working. In 0, in 1, and the next one's up on C0 and C08. Our dip switch was up at C18, and then our ROMs, the ROM enabled general ROM is there from 600 up to F800, so that's good. And then each individual chip was selecting at 6, 680, 70, 780, and then again repeated for the E to F. Then that's for everything with write not enabled. And then when we enable writing by it being low, then we are into basically the RAMs are still able to write, obviously, so we still have our RAMs at these lower ones. And then we have our out instead of ins being enabled at our Cs. Now when we get to our ROMs, you'll see the ROMs aren't activated because our RW is low and our NWO is high, so it's not activated. And then the other ones we've got are interrupt acknowledge and our watchdog reset, our outputs, watchdog reset 0C18, and that becomes low when we've got write enable low and we're at that C18. So that's that simulator. And then the second simulator is everything just back to normal. And then what I want to do is just run the code. So this is now all grayed out, the address driver, and we've got our CPU back as active. And we're going to run Modelsim, and we're just going to see what it's doing in terms of the code, and see is it actually going to be, we can monitor the output of the color and see if we're getting anything. Okay, so I have set everything up in Modelsim and I've let it run for a little while, and we can see here how everything's working. So just like we had before, this is our reset vector, FFFC, FFFD, except in this case what happens when it goes to there, it pulls in 4, 3 and 7D. So it's our CPU data in. It's taking it in from our ROM 1D, which is our highest ROM. So it's gone 4, 3, 7D, and that's what's input. And because of that, it goes to that location. That's where the program starts. And then it starts running. And what it's doing is it's effectively going to start clearing some area in the 0 page. So we can hear straight away in address 0001 we have a write enable, so we have an active low write, and it's writing 0C into that RAM location. So we'll step through in a bonus video what the startup sequence is doing in this game, and have a look at the assembler language. But I just wanted to show this a little bit, just to show the startup. And effectively what happens is later on, when it's run a little bit, we start to get colors. So you can see we're getting this display DIN is actually outputting something, and that's then going into the display circuitry. So we can see all these colors coming through. Those output colors obviously translate to what our picture on the screen. So everything's working here. We're super happy with that. Now it's time to go into Quartus and then compile and run that too. So depending on the flavor that you want, either the CRT or the VGA version, remember with the VGA, it's not outputting through the HDMI port on your MiSTer, it's still outputting from the VGA port on your I/O board. It just goes straight into the VGA for you there, so not through the HDMI. So the CRT version, download this file, stick it into Quartus, compile it, and then what happens when we run it, we will get a very nice test screen coming up. There it is with the changing ROM pattern, and then it goes through a little bit of an attract mode where it's counting up the amount of points, and then it takes us a certain way, and then it freezes because we haven't implemented the interrupt. So basically it's just catching there. Really can't get over how happy I was when I first saw this working. It was the first core I've ever properly done, implemented, and when you see it actually working on the screen, it just absolutely blows you away. Super happy. I obviously had another bug to work out because of this freezing. Now I'm implementing the circuitry as we go along, but when I first did it, I tried it kind of out all straight away, which I wouldn't recommend because you end up getting lots of bugs. Doing it step by step like we're doing is a much better way of doing it, so you can totally understand everything as you go along. With the VGA version, we on my VGA I don't get time to actually see the cycling of the RAM pattern. Goes straight into that pattern there, and then we get that same counting up on the points, and then into the frozen attract mode. But that's good too. It's good we've got a VGA version there. So coming up in the next one, what we're going to do is we're going to start looking at that bullet circuitry, and it's quite interesting how it does it. So something to get our heads around. We'll spend an episode doing that. We'll implement it in the Verilog, and then once that's done, it's a short process to then add just a little bit more interrupt enables. That'll get the code working, but we won't have any controls. And then we can put it into the MiSTer framework and get it going. So looking forward to it. See you next time.